and circuit.
When water flows in a river from a higher level to a lower level, forming waves, it is called a current of water. Similarly, if we make electric charges flow by applying a force, a current of charges is created. The flow of electric charges under the action of a force constitutes electric current.
Activity: take a torch, take out its cells, and try to obtain light. Is it possible to get light? No. Can you tell why? This is because cells are the source of electricity, which makes the bulb glow. Take two small copper wires and join its ends to a small bulb. Join the other two ends of the wires to a dry cell. Observe the bulb. The bulb glows. Here the electric current generated by the dry cell flows through the copper wires and hence through the bulb. The current passing through the bulb makes it glow. Take out any one end of a wire connected to the cell. Observe the bulb. The bulb does not glow since one end of the wire is disconnected from the cell. This shows that the wires should be connected between the cell and the bulb to make the bulb glow. Hence, a closed path is required for the current to flow in the wires and the bulb. The closed path through which electric current flows is called as a circuit. Let us understand what makes the electric current flow in a circuit.
Matter is composed of atoms, and every atom has protons and neutrons present inside its nucleus. While the electrons revolve around the nucleus in their fixed orbits, only electrons can move from one point to the other, unlike protons and neutrons, which are fixed inside the nucleus. In some substances, like metals, the electrons in the outermost orbit are loosely bound to the nucleus and can easily be detached from the atom. These electrons move randomly in all directions and are called free electrons. When a force is applied and these free electrons are made to flow in a particular direction, they constitute electric current. It is interesting to know that metals contain a large number of free electrons moving randomly in all directions, which are readily available to constitute electric current. Electric current is defined as the rate of flow of charges. It can also be defined as the amount of charge flowing through a conductor at a given point per unit time. If Q is the net charge flowing through any cross-section of a conductor in time t, then current I is given by I is equal to Q upon T. The SI unit of charge is coulomb and is symbolically represented as C. The SI unit of time is second. Hence, the SI unit of electric current is coulomb per second or ampere, which is named after French physicist
André Ampère.
The instrument used to measure current is called an ammeter. The electric current in a conductor is said to be 1 ampere when a charge of 1 coulomb passes through a given point in 1 second. That is, 1 ampere is equal to 1 coulomb upon 1 second.
Small values of currents are expressed in milliampere and microampere. 1 milliampere is equal to 10 to the power minus 3 amperes. 1 microampere is equal to 10 to the power minus 6 amperes. While large values of currents are expressed in kiloampere and megaampere. 1 kiloampere is equal to 10 to the power 3 amperes. 1 megaampere is equal to 10 to the power 6 amperes.
Direction of electric current. When electricity was invented, scientists were known that there are two types of charges, positive charges and negative charges. But during that time, electron was not discovered, and it was believed that electric current results only due to the motion of positive charges from a positively charged object to a negatively charged object. This direction of flow of charges was thus taken as the direction of electric current. Thus, the direction of conventional electric current is taken from the positive terminal of a cell to the negative terminal through an electric circuit.
Drift speed of electrons. At room temperature, the free electrons in the metal wire move randomly in all the directions when no electric source like a dry cell or a battery is connected to the wire. When a source of electricity like a cell or a battery is connected between the ends of the metal wire, An electric force acts on the free electrons present in the wire, making them to move towards positive terminal of the cell or the battery. The electrons gain velocity in the direction of the electric force. This velocity gets superimposed on the random velocity of the electrons. As a result, the electrons in the conductor move with a certain average drift speed towards the positive terminal of the cell or the battery. This flow of electrons constitutes the electric current in the wire.
Let us solve some numerical problems based on the topics we have studied.
Problem 1. A current is of 0.2 ampere is flowing through a bulb for 5 minutes. Find the charge that is flowing through the circuit. Solution. Let us first write given quantities. Current I is equal to 0.2 ampere. Time T is equal to 5 minutes, which is equal to 5 into 60 seconds, which is equal to 300 seconds. We have to find total charge Q flowing through the circuit. It is given by Q is equal to I into T. Substituting given values of current I and time T, we get Q is equal to 0.2 multiplied by 300. Therefore, Q is equal to 60 coulomb. Hence, the charge flowing through the circuit is 60 coulomb. Problem 2. A charge of 420 coulombs is flowing through a circuit for 10 minutes. Find the current in the circuit. Solution. Let us write the given data. Charge Q is equal to 420 coulombs. Time T is equal to 10 minutes, which is equal to 10 multiplied by 60 seconds, which is equal to 600 seconds. Let us find the current I flowing through the circuit. It is given by I is equal to Q upon T. Therefore, I is equal to 420 divided by 600, which is equal to 0.7 ampere. Therefore, the current in the circuit is 0.7 ampere.
Problem 3. Calculate the number of electrons constituting 1 coulomb of charge. Solution. We know that the charge of an electron is 1.6 into 10 raised to minus 19 coulomb. Now, if charge is 1.6 into 10 to the power minus 19 coulomb, then number of electrons is equal to 1. So, if charge is 1 coulomb, then number of electrons is equal to 1 upon 1.6 into 10 to the power minus 19 into 1, which is equal to 10 to the power 19 divided by 1.6, which is equal to 10 divided by 1.6 into 10 to the power 18, which is equal to 6.25 into 10 to the power 18. Thus, 6.25 into 10 to the power 18 electrons taken together constitute 1 coulomb of charge.